Right, so it's recording now. So this is lecture number 31, the second in the module on GPU parallelism. So yesterday we had a brief discussion on the introduction in terms of why use GPUs and why are they timely for this discussion on a course on high performance scientific computing. And we started with some basic ideas of how to write a CUDA C code that is for adding the terms of a vector. So we'll continue with that. Let me do a quick recap of the problem. Well, we said that in a CUDA C code typically you have, or CUDA code, could be CUDA C or CUDA Fortran, you have two types of codes. One is a host code, the other is a device code. Host is the one that is written for the CPU and device is typically your GPU. So device code is basically the code that runs on the GPU. So you write the functions for GPU execution, which are called kernels. So kernels are the functions which will typically have the parallelized work which will run on the GPU. So execution typically starts with the CPU in the form of a sequential code. You have some data which is available in arrays on a host, and then you copy that to the device. You do some work and then you copy the data back to the host and use it, whether you want to print it on the screen or you want to store it in a file, whatever. And you may have this launching of threads through kernels on the device happening multiple times. So every time you launch, you say you have launched a grid. So grid is basically a collection of threads that you launch on the GPU. So these are just terms: kernels, grids, device, and something that you have to get used to while working with GPUs. So this is the vector addition kernel or the vector addition program that we had started discussing yesterday. So what we have here is we have this is a hello world code for CUDA. So I mean, the one that you see in front of you is basically a traditional code that you would write on a CPU. So you pass on three arrays, A, B and C. So A and B will be added to result in a C. So C is equal to A plus B in this case, and you also pass the number of terms in the arrays in the form of an integer n. But let's see how you write it in to send it on a device for GPU parallelism. So you write in three parts. Part 1 is responsible for allocating space on the device's memory. As we discussed yesterday, that the device or the GPU has its own memory, dynamic RAM. Then once you have allocated space on the device, you have to copy the arrays from your host to the device, because initially the information about A and B are sitting on the host. And once you have the information available in arrays on the device memory, you launch threads and perform the computations. And then part 3, the last part, is to copy the data from your device memory. In this case, that is the variable C or the array C, copied back from the device to the host, and then you use it in whatever way you want. Okay. So we had showed you parts 1 and 3. So in this case, for allocating space, we use, I mean, the naming convention typically is such that you use an underscore D or D underscore. So sometimes you will say A underscore D, or sometimes you will say D underscore A. Basically, it means that these are arrays which will be available on the device memory. And if you have A underscore H or H underscore A, these are arrays that will be available on the host memory. So in this case, this function typically will take in host memory array pointers for A, B and C, and then it will define arrays on the device memory. And the way you define memory on a device is using this function called CUDA malloc. This is CUDA C that we're talking about, and then you pass in the reference to the array on the device memory, or the pointer on the device memory, and the size in bytes as well. Okay. We do this memory allocation for the three arrays, then we copy the information from the host to the device. So use this CUDA mem copy function, This function is used for both cases, for copying the information from host to device as well as from device to host. So, you have to specify this constant which is CUDA mem copy host to device, which tells the function that you want to copy the information from host to device in this case in part 1. Then the last part 3 is simply copying the data back from your device to host, and finally you free the space on your device so that you can use it again for when you launch the kernels again. In case you do not free it, it may happen that you may go out of memory very soon. So, it is very important to free the memory as well. Okay. And I also mentioned that you should not try to reference the arrays which are defined on the device memory from a host. So, remember there is a host code and there is a device code, and we will discuss that in more detail, but this is what you see in front of you is a host code. It is not running on a device, it is running on host. So, you should not be trying to find or iterate through array locations of for the pointer a underscore d, b underscore d or c underscore d here, otherwise bad things can happen. Okay. Just be careful. Right. So, this is what we discussed yesterday, and what you see now is fresh content from for today. Typically, we also have error checking like we discussed in Python. So, also it's always good because you're dealing with API functions, and it may happen that sometimes allocation of space may fail, or copying the information from host to device or device to host may fail, or something else may fail. So, it's always good to do some error checking. So, here what we do is we have an object called ERR, which is basically returned from the CUDA malloc function, and this should be ERR, not error. So, you just check if ERR is not equal to CUDA success. Again, CUDA success is some constant, you do not need to worry about that, that is already available in the import statements. So, all you have to say is that when you run this CUDA malloc function, rather than simply saying CUDA malloc, you should do it this way. So, this CUDA error underscore t variable class's object ERR is equal to this. So, this CUDA malloc returns an object, and then you check whether this is equal to success or not. So, if it is not equal to success, that means it has failed, and then you have to print something and you should exit. Okay. Again, these things can be explored in more detail when you want, but I just want to convey a message that typically you should, once you are happy with these things, you should start putting in error checks to ensure that the code, if it fails, you get out of it and do not continue with something which may lead to something unintended and you get confused. So, let us talk a bit about a thread hierarchy, although we will go into much more detail later when we talk about the architectures and so on, but for the first level discussion for this hello world code, we need to understand some level of hierarchy. So, in CUDA or in GPUs, typically you will see that when we say you launch a grid of threads, between having a grid which is a complete collection of all the threads and threads which is the smallest unit of computation on a GPU, there is a collection of threads called blocks. Okay. We will discuss more in detail as to why and what is the meaning of having a block of threads or thread blocks, but for now just understand that there is something called blocks. So, what you will have is your complete GPU codes will be distributed into blocks of threads, right, and each block will have some threads. So, a block can contain up to 1024 threads, but it can have lesser than that as well, and that is actually your choice as to define the number of threads in a block. So, if once you write a kernel function which is going to run on each and every core of a GPU, you have to specify with that function the number of blocks you want to launch and the number of threads per block that you want to launch. So, that is your choice. So, for example, in this case I have written this statement which is used to launch a kernel. It is like when you call a function, right, it is a function definition where you define a function and then you execute or call the function later. So, that function call is this vec add kernel, but what you see is that it is very similar to a standard function call in any programming language, except that you have these 3 fishbone characters with n blocks and n threads. So, you have to specify the number of blocks you want to launch and the number of threads per block. So in this case 256 is basically the number of threads per block that you want to launch, and you cannot go beyond 1024 as of now. Okay. So this is something you have to specify as a programmer. Of course, you can have variables which will contain value depending on some n. I mean, you don't need to hard code it in the program as such, but still you have to specify the number of blocks and number of threads per block. So the total number of threads will be the multiplication of these two numbers. So the total number of blocks multiplied by the number of threads per block will be the total number of threads you are launching in your kernel in the grid that you launch for GPU computations. Now the interesting thing is that these blocks need not be one dimensional, in the sense that like I say there are 10 blocks, or I mean let's look at this 1D example in front of us, and then we'll go into discussing n dimensional systems. So let's say you have a total of n blocks. Okay, so the numbering of the blocks will be from block 0 to block n minus 1, right? Each block in this case has 256 threads, as I've shown in this kernel call. So the numbering of the threads will be from 0 to 255, and each block's thread numbering will be from 0 to 255. So the thread numbers are not unique, as they start from 0 and go all the way to the number of threads per block for each block. Is that clear? And if ultimately you are doing a data parallel job, right? So what happens is that you are running the same code on all the threads, but each thread should be working with a different data point. If they work with the same data point, then there is no point of launching the thread, you are just replicating the work. So to use the idea of data parallelism, where it's the SPMD approach, where you have the same program but you have different data running on each thread. So if you are working with an array where you are adding elements, you will need an I, the index of the array, which has to be unique for each thread. So how will you convert the block numbers and thread numbers into that unique index numbering? So we have this formula here, where I is equal to the block ID. So block ID is going from 0 to n minus 1 times the block dimension. Block dimension is basically the number of threads per block. So if you are working with block 0, then this is 0 times 256. Okay, if you are working with block 1, this is the block ID is 1 here, and block dimension is simply the number of threads per block, which is 256. So 1 times 256 and so on, and then you add the thread index as well. So thread index is going from 0 to 255 in this case. So let's say we are working with the second thread here in block 0. So it takes the index 0 times 256 plus 2, that is I equal to 2. But if you are working with this thread, thread in the block 1, then it takes the index 1 times 256 plus 2. So that's 258. So basically what's happening is you're counting threads from here, you go from 0 to 255, and then you start calling this 256 and so on. So that results in the index I having a unique value. There's nothing complicated here. I'm just typically that's how you deal with working with systems where you have structures where you have a block and a thread and so on. Okay. So once you have defined an index I in a unique sense, in the sense that each thread will have a different index I with this formula in terms of block ID and thread ID, then you can simply say CFI is equal to AFI plus BFI. And remember, GPUs are very powerful when you work with light computations, but lots of these. So that's what you're doing here. You're simply adding two numbers into another variable, adding two variables into another variable. In this case, A of I and B of I are added to give you CFI, and this calculation happens on each core separately for each index I. Okay. So now that the idea is clear, let us see the complete kernel function, because we haven't seen the definition of the function yet. So let's have a look at that. So let's look at this code. So let's look at lines number 4 onwards. So in line number 4, you see that you have defined this vec add kernel. So that's your function, and we use the word kernel just to make sure that you understand that this is a kernel function, in the sense it runs on the GPU. It does not return anything, so its return type is void. That's how you return nothing in C or C++. Then what do you pass to it? You pass to it 3 variables or 3 arrays, A, B and C, and the size of the arrays, which is an integer n. Now remember, this is a kernel. This is a kernel function. By definition, it runs on GPU. So we don't have to specify A underscore D, B underscore D and C underscore D in the definition. It's understood that whatever is passed to the kernel is going to be the device memory, because you cannot access host memory from a kernel function, because kernel function runs on the GPU. Alright. So we pass in these 4 objects, and then as we saw in the formula, the integer I, which is a private variable in this case for the GPU, is calculated as the thread index. I'll talk about this dot x, dot y and so on later. So let's just ignore this. We say that integer I is thread index plus block dimension times block index, the same formula we just discussed, and we have this if condition. If I is less than n, you do C of I is equal to A of I plus B of I. And the question is, why are we having this check for I less than n? Because what is n? N is the number of elements in the array. Of course, you don't want I to be going beyond n or equal to n, because then you will try to access C of n plus 1 if it does not exist. So that can cause that can result in you trying to access memory which is not available to you, and the program can crash, or it can do unintended things. So you want to make sure that you refer to the index locations on arrays which are available to you. So this is very important. But the question is, why would I, the index, go beyond n? Now let's look at the figure again, where you have blocks and indexes. So let's say your number of threads per block is 256, and you have only 2 blocks. So block 0 and block 1, that's it. So if you define 2 blocks with each block having a total number of threads as 256, what happens is your total number of threads available to you is 256 times 2, that's 512 threads available. But your n could be 500, for example. So that means that 12 threads will not be doing anything. They just are defined because of the structure of block times number of threads per block. Okay, and typically this number of threads per block is a multiple of 2. So what happens is that some of the threads will be sitting idle. So to take care of the situation where the number of threads in total is greater than the number of indices you want to work with, you have to specify this if condition. Okay. Now you also see that in line number 3 you have this keyword called underscore underscore global underscore underscore. So what is the use of this? So this keyword helps denote that this kernel function is called from the host and it executes on the device. Okay, so kernel functions are basically, the host will call it, the CPU, because the code is executing serially on a CPU, and then it calls the function, it will call the function. So the function will be called from the host, and it's a kernel function, so it will execute on the device. So this keyword helps the CUDA compiler understand that yes, this is indeed a function, although the function has a name kernel, but that is just for naming convention. The compiler does not understand. You could have you could not put a kernel name here, still it remains a kernel function because you have the keyword global before this. By the way, this global can also be in the same line, it's just in a separate line to understand. So so if there is a global, there are other keywords available as well. So you have a keyword called host, for instance. So this keyword host, it basically says that this function is being called from the host and it will also execute on the host. That's a standard CPU function. Then you can have something called a keyword called device. So these are functions which are called from the device. So a kernel function could have been calling another function. So if a kernel function calls another function, since the kernel function is running on the device, so then that function will have to have the keyword device before it, because these functions with keyword device are called from the device, that is on the GPU, and they execute on the GPU as well. So we may not see programs where we use this idea of device keyword function with device keyword, but it's important to know these things, because when you start working with more advanced ideas with GPU programming, you should at least be able to understand what is happening there, and then it will take some more time for you to graduate into being able to write functions or structure the functions in such a way so that you can have a mix of host, global and device functions. But typically you will have functions which are either host functions or global functions. So functions which are running purely on the CPU or functions which are running on the device but called from the host. And you see this variable I. So this is a private variable in the sense that you are defining this variable inside the kernel function. Okay. So what that means is that because you want I to be private, because each thread should have a separate I value. That's the whole idea, right? So if you have a variable being defined inside a kernel function, then that variable becomes private. So we call it an automatic variable or a local variable. I'll tell you why it is called a local variable, because there's an idea of local memory. But anyways, I mean, it's called an automatic variable which is private to each thread when it is included in the kernel definition. Also note, there is no loop here. Typically when you have lots of indices of an array, you have a loop. Like if you look at the CPU program, then what we had was, we had for I equal to 0 to I less than n, I plus plus, there is C of I is equal to A of I plus B of I. But now in the kernel function there is no loop, and the reason there is no loop is because this is running on all the threads. So loop is for sequential operation, right? But what's happening is that you are giving one index I to each thread. So this code kernel function runs on each thread. You already spawn threads, then you run each I is execution, that is A of I is equal to A of I plus B of I equal to C of I on each thread. Okay, so there is no loop required because the work is parallel, it's not sequential. And unlike CPU based parallelism, where we saw that you give a bunch of I values to each core in a CPU, I mean, we said that there should be some minimum amount of work available for each CPU. We never did something like, there are 24 cores, let's give each element of an array to each core. But in GPUs, they're meant for these light computations, lots of light computations. So you can give each index I's work to each core. Okay. Now you see that we always had this dot x in the thread ID, dot x in the block dimension, which is basically the number of threads per block, and dot x in the block ID as well. So what is the meaning of this? Now what I showed you in this figure is a one dimensional case, but on GPU you can also have things in 2 or 3 dimensions. So let's say you are dealing with a matrix, a 2D matrix. So in that case, how will you distribute threads? So what you can do is, you can generate blocks which are 2-dimensional blocks. Again, I'll discuss more about that later in more detail for multi-dimensional data, but I just want to tell you that blocks can be 1D, 2D or 3D. So 3D is like, you know, you will see blocks in X direction, blocks in Y direction, blocks in Z direction. So that very naturally will fit the dimensionality of the data. So if your data is 2D, like if you're dealing with 2D matrices, adding 2D matrices, then you can generate 2D blocks and each block has threads in 2 dimensions. Okay, so you can have, then you will have this block id.x and block id.y, because you have blocks in X direction and blocks in Y direction. Similarly, if when you have threads in 2 dimensions, then you'll have thread idx.x and thread idx.y. So each block will have threads in both directions, and this can also happen in a Z if you have 3-dimensional matrices. So when we deal with systems which are, you know, solving let's say flow in a 3-dimensional world, then you distribute your space into blocks, and each block has coordinates which are, so if you're dealing with this room, for example, I want to calculate the temperature or velocity field in this room. So very naturally the data which is actually 3-dimensional, because you have coordinates, spatial coordinates in x, y, z coordinates, then your data can also be represented using these data structures which are 3-dimensional. So that matches very well with the dimensionality of the data. Again, we will come into that later. So this is, now that we understand all 3 parts, part 1 which is allocating space and copying data on the device, part 2 which is doing the computations through the kernel function, and part 3 which is copying the data back and freeing up space on the device. So this is your complete code which is executed on the host. Okay, so let's look at it again. So lines number 2 and 3 are simply telling us what is the size of the arrays, because you want to call the CUDA malloc function in lines 5 to 7, where you allocate space for device arrays A, B and C. Then line number 9 and 10 will copy the data from the host to the device, and then the part 2 starts, which is line number 12, where you call the kernel function. So this is the function call, and the function call will happen on the device because it's a global function. We just showed you in the previous case, this is the function definition for the kernel function, which is a global type. So that means it will be called from the host, although it will run on the device, but the calling will happen on the host. So line number 12 here is where you call this function with some block size and number of threads per block. Now how do you decide? So number of threads per block we decide beforehand, let's say 256, and again we will discuss more about how to decide these things, but let's say 256. So once you decide the number of threads per block, deciding the number of blocks is easy now, because you know the total number of elements in the array, which is n. So you simply divide n by 256, and if that's a fraction, you go for the higher integer value. Okay, so if the total number of let's say n is 500 in this case as an example, so number of threads per block is 256, so you need 2 blocks. So if you divide 500 by 256, you get 1 point something. So the ceil function basically is a ceiling function, so it takes the next integer, which in this case will be 2. So you will have 2 blocks and 256 threads per block. Okay, and what do you pass to this function? You have to pass A, B and C, but you have to pass A, B and C which are device memories, because this is happening on the device. You already have copied the data on the device arrays, so you have to pass these device arrays to the function along with the value of n, and this will do the job. And after the function is executed on the device, of course, your C_d will have all the answers. So now you execute part 3 in line number 14, where you copy the data from the device back to the host. So after line number 14's execution, your host memory will have your C_h will have all the information with it. In this case it is C. Okay, so this C is the host memory. So you have copied the device memory to host memory now, and then you can do whatever you want. So once this function is executed on the host, After that, you can print the values of C on the screen. Okay, and you have to free the memory as well on the device. That's very important. Okay, so these number of blocks and number of threads per block, they are called configuration parameters. Again, another terminology. So these configuration parameters are to be decided and to be passed on by the programmer, although you don't need to hard code them. They can be in terms of some other variable, like in this case in terms of n, but it has to be specified. Right. So before we actually show you a demo by running a code on the GPU on this laptop, let's discuss a few notes. So one is all threads operate the same code as we have discussed, but work with different data. So that's the SPMD approach, single program, multiple data. The other thing is, although you don't need to be worried about that, but blocks can execute in any order, and that's okay because it's a parallel job, right? You don't expect them to be happening in any particular order. If that is the case, it becomes a serial job. So parallelization means that all of them can run together, but it can always happen that some threads are faster than the other or some blocks are faster than the other. So you don't have control over which blocks execute in what order, and that's completely expected because it's a parallel situation. And that's good because if your GPU is small, let's say your GPU can only handle 2 blocks and you launched 4 blocks. So what will happen is it will execute these 2 blocks and then it will execute the other 2 blocks later. Okay, but which 2 blocks get executed first, it's not in your control. So it could happen that blocks number out of 4 blocks, blocks number 1 and 4 happen first and 2 and 3 happen after that. Okay, and that's a good thing because if you use the same code on a bigger GPU, it can run all of them together. If you run the same code on a smaller GPU, it just runs the blocks in such a way so that you have to do sequential operation depending on how many blocks can fit at one time on a small GPU. Okay, and the most important thing is that allocating device memory, transferring data from host to device, and then transferring back the data from device to host and deallocating memory, all this has overhead associated. So before jumping into parallelizing things, you should do some experimentation whether it is worth doing that, because it can happen the overhead of all these things can be much more than running simply the code on a CPU sequentially. Of course, I mean, we are parallelizing, so definitely it works in some cases, but for example in this case it may not work because the amount of computation you are doing versus the amount of memory movement that you are doing is not very high. You are simply adding 2 numbers, but you are allocating space, copying data and then copying data back. So in fact what we do is we take a ratio, and I will discuss that in the lectures to come, that we always take a ratio of the number of floating point operations you are doing to the number of memory transfers you are doing, and if that ratio is large, it makes more sense to do the parallelization on a GPU. Okay, but I will give you some examples where you will calculate the ratio and see whether it is a good situation to parallelize or not. So let's do some demo. So let me show you the steps. So typically if you want to run this on a system from scratch, the first thing you do is you have to install the compiler. So for Fortran we use G-Fortran compiler, but we saw that when we had to use MPI, we had to use a different compiler, which was MPI F90. So here typically for C codes you use GCC or G++, but since it is CUDA code, so you have to use an NVCC compiler which is available from NVIDIA. Okay, that's called the NVIDIA toolkit that you have to install on your machine. So you can just Google it and install, that's very easy. Then you can verify using this command nvcc ---- version. If it runs, it prints something, that means it was able to install it. Then you have to write a code and save it. In this case we have already saved the code in, by the way, the code is available on your repository now, so you can go and have a look at it in a folder called CUDA. So this code is vector underscore add and the extension is .cu for CUDA codes. You have to open the PowerShell for Visual Studio. Is just basically it's a command prompt which has all the things installed in it, so you don't have to worry too much about it. Just open it and you have to write the command for compilation, and then you can run this using the executable. So very similar idea. Now what is a command for compilation? You have this nvcc command, then you specify the code name vector underscore add.cu, then you specify the output or the executable name, which is vector underscore add.exe. So very similar to the way we had run the gfortran command, except that you also specify this flag called -arc, which is architecture. Now the GPU cards, as I told you, the hardware design is also changing over time. So these are called architectures. So we will discuss more about these architectures later, but that figure I showed you where you had a memory, a DRAM in a GPU, and then you had lots of cores, and a collection of cores had their own private memory as well. So this is an architecture. Now over time architectures change. Some of the architectures may have some tensor cores available and so on. So you have to tell the compiler what is the nature or the architecture of my GPU card. So it's a family of architectures, a family of cards falling under the same architecture. So once you tell the compiler knows that yes, you have some tensor cores, you don't have some tensor cores, and how does the design look. So it's much easier for the, or it's actually, if you don't specify it, in most cases it will not work. So in my case the architecture is 8.9. So I've put a slide here with NVIDIA architectures. So all you have to do is you have to Google basically. So in my computer I have the RTX 4050 card. It's a very standard gaming PC card. So this falls in the compute capability 8.9. Okay, so this has a name called Ada Lovelace, okay, who was a scientist, a computer scientist. So this and the other cards which also fall under the same architecture. So this 8.9 it's called a compute capability. So this 8.9 is written as SM_89. Okay, so there are different codes for different architectures for this NVCC compiler. So you figure out which architecture. This is the latest one, H100, that I talked about. That's a Hopper architecture. And you may also see A100 card, which is an Ampere architecture, and so on. The V100 that we have on Param Himalaya is the Volta architecture. So you'll have to specify 70 when you compile the code on Param Himalaya. Okay, so you have to be careful with that. And there's also which version of CUDA is supported. So for Ada Lovelace, for example, it's CUDA 12.2 or onwards which supports this architecture. Anyway, so let's do this. So I'll open a command prompt, and as I said, you have to open a developer PowerShell for Visual Studio 2022. Just open it. So this basically is a command prompt which has all the paths set up for the different tools you need to compile this code using NVCC. So now you have to go to a folder where we have this installed. So in my case, the CUDA codes are available. In a folder called CUDA codes. Okay, so I'll go to that folder. And when I do an ls, I have this vector underscore add.cu. That's the. So those at the very back, can you see the screen? I mean, can you read the stuff on the screen? Okay, thank you. So this is the code that we have to execute or compile in this case. So let's have a look at the code. Let's open in Visual Studio Code. You'll be able to see some nice highlighting there. So this is the code, the complete code written in CUDA C. So you include some modules. So you have some include statements, standard input output, CUDA.h and Windows.h. Windows.h is simply for a sleep statement that is not needed as such. You define n, which is basically a constant, which is the size of the array, and then you have the definition from lines number 7 to 11. You have the definition for your kernel function. So in this case, you see that I have not included the kernel keyword here. That's not required. Okay. So you just have to put the global underscore global because that tells the compiler that this is a kernel function. You define an index. In this case, it is idx. In the slides, it was the index I, and then you write it in terms of the block ID and the thread ID, and then you have an if condition in line number 9, which basically ensures that you don't go beyond the. You have more threads in this case than you could have more threads than the number of indices. You just have to make sure that you only use the threads which are required and leave the threads towards the end which are not required. Then we have the main function starting line number 13, where you do the part 1, which is to allocate space on the device and copy data from host to device. And once you have done that, so here we also have to initialize the host memories. So basically here what we are doing is we are allocating the memory on the host first. Okay, that is also dynamic. We never talked about that in the slides. So once you allocate the host memory, it's not CUDA malloc, it is malloc here. So that is for host memory, and then you initialize that with something. So we just put some dummy values in the arrays that we'll add later. Now you copy this onto the CUDA memory, and you allocate memory on CUDA in lines 27 to 29, and line 31 to 32 you copy the data from host to device. Line 34 you set the number of threads per block as 256, just as in the slides. Then you define the number of blocks per grid using a slightly different formula, but doing the same thing as in the slides. Then you call the kernel function in line 36 with the configuration parameters, that is blocks per grid and threads per block. Here you do some error checking to make sure that CUDA was able to launch the threads on the GPU. If not, it prints an error and exits. Then I have a sleep statement just to hold for 5 seconds, because later I would want to show you that this is running on the GPU card. So to show that the program runs very quickly, just a very basic computation. So it's very difficult to figure out whether the program actually ran on GPU or not. If you sleep for some time with some memory allocated on GPU, you will see the GPU memory being used for a few seconds. So then that is a check whether the program is actually running on the GPU or not. Then finally you copy the data back from your host of your device to the host. And then for a few indices we print the values of the host arrays. So if things worked fine, you will see that the host array C will have the right values, which is A plus B for those indices, the first 5 indices in this case. Finally you free the CUDA memory and you also free the host memory. Okay, so let's run this code. So NVCC, and as I said, you have to specify the architecture. So in my case the architecture is SM_89, and then you specify the code then the executable, and we run it. So now it generates the exe file. In fact, I can do an ls and see this exe has been generated. It's been generated at 9:50, which is right now. So we run it now. So it will do all this on the GPU card, and finally it should give me the value of C. So for just a few indices, I am printing the values of A of I plus B of I is equal to C of I. So you can see that A of I plus B of I is indeed equal to C of I. If the host memory was not able to copy the data back from the device, or device memory did not do the work properly, this would be wrong. But this is correct. Okay. So the way we had defined A and B was A was increasing from 0 to n and B was decreasing from n to 0. So the sum of A and B is always equal to n in the example. Okay. And to see whether it actually runs on the GPU or not, I can go to task manager and I can go to performance, and in this case I have two GPU cards. One is an onboard Intel GPU and the other is NVIDIA GPU. So I can just go to my NVIDIA GPU and you see it's already using some memory because it's doing some video encoding, because I've connected multiple screens. So one of these, I think the projector one, is being managed by the NVIDIA GPU card. It was meant for pixels, right? But let's see if I run this code, if something, you see something happening on the card. So now the code is running and you can see that there is some copy operation that happens, right? See a slight bump here because this code is very basic. So there is some copy that happened on the device memory, and if I did not have a screen connected, I would see a small, in fact you can see this small increase here. So that is your dedicated GPU memory increased a bit. So the constant one right now is for this video encoding, but if I run it again, you might see another bump happening. That's because the program is now running on the GPU. Is that clear? Right, so it's time now, so we'll stop, but I suggest if you have the hardware available, if you have an NVIDIA card, if your friends have it, just try the code out. I know you cannot run it without an NVIDIA card, but Param Himalaya is available to you, which has an NVIDIA card available, so you can always try this on Param Himalaya. And starting next week, I'll talk about how to run this CUDA, a very similar code, run it in Python, but the Python code is already available to you, so you can have a look at it before you come to the next class. Thank you.